Hi, folks. Welcome to this first meeting of Geology 1500, section 604. So this is an online asynchronous class here. And what that means is that I'm doing these lecture recording sessions, and they'll be happening on sort of Monday at 10 a.m. here and at Wednesday at 10 a.m. But the class is set up to be asynchronous so that you don't have to record these things, or you don't have to attend these. The lectures will be recorded and then they'll go online on Canvas, but you may find it useful to actually watch these things live because then you can ask questions, you can interact a little bit, and that can aid in your learning. And so I'd encourage you to show up here if you can. But like I said, due to the nature of the course, that's not required here. So what we're going to be talking about this semester, the name of the course is Dynamic Earth, and really what we're going to be doing is we're going to understand how basically our planet works. And that's really the goal of the course. And so we start with big picture ideas, thinking about where the Earth sits in our solar system, where it sits in our galaxy, our universe, thinking about these really big picture ideas. And then we think about how basically our planet has formed, what's its basic composition. Then we'll talk about ideas like plate tectonics, and so forth, which is this idea for how our planet functions. The basic idea is that you have sort of a limited number of plates that move around sort of on the surface of a planet. Then we'll go on to talking about sort of rocks and minerals. These are basically the language through which the history of our planet is written. And so if you understand basically how different rocks and minerals form, it can tell us something about sort of the history of our planet. It can tell us about processes, important processes. And so if you understand what has happened to our planet in the past, we can better help us understand what's going to happen in the future. And that's sort of the first sort of half of the course. The second half of the course will focus more on surface processes, different geologic processes that happen in sort of different climatic conditions, things like deserts, glaciers, coastal environments in here. We'll also talk about climatic change, how these basically how things have changed in the past, how they may change in the future. We'll also talk about energy resources. And so this is one of the things I'm going to emphasize throughout the course, is that geoscientists are involved in understanding basically how our planet functions, but they're also involved in finding resources that are necessary for our civilization. So that's sort of a brief overview of the course here. What we're going to talk about today is, first I'm going to go over the syllabus a little bit, tell you about sort of the nuts and bolts of how our course is going to function. And then I've got a lecture really on the nature of science. And so what science is an important place to start, and this is a general education course. And so understanding the nature of science and what science is almost more important than any individual so forth topic that we discuss throughout the semester. And then we'll also finish off by talking about where basically the geosciences, the earth sciences fit into sort of the different scientific disciplines in general. I also want to point out that if any of you have questions during these lectures, you can basically ask it sort of verbally. You can also type it into the chat. I'll try to monitor these things and then answer basically any questions that you have. And so that's one of the advantages of, like I said, of attending these things live. Oh, so another question. That was, so the question is, I have another class that starts at 11 a.m. This meeting doesn't end until 11:20, hoping that I could leave a little bit early. Yes, that's fine. This, like I said, this whole session here is recorded. It'll go on Canvas, and so you can watch any of the section parts of this that you cannot attend live. You can watch it basically remotely at your convenience. And so that's, I guess, one of the advantages of basically the online nature of this course. So any other questions about basic scheduling and so forth? Okay, so what I'm going to do first here is I'm going to share my screen. We'll look at some of the syllabus here. Okay, so the syllabus will be posted on Canvas. It's not yet. I need to add some scheduling information, sort of a sequence of topics and so forth. It's not quite finished yet, but hopefully you're all here for Dynamic Earth, Geology 1500, section 604 in here. And really, this is an introduction to the geologic sciences. And really, our goal is to give you an idea of how the Earth functions and what are sort of important processes on our planet. And these are important because we live on Earth, and it behooves us to understand how our planet functions, so that we can properly use sort of the resources here, and we can not damage our environment, and so that we can pass on basically a good environment to basically posterity in here. And also basically understanding where geologic resources come from is important for basically our civilization. So there's a number of different reasons why you should be interested in the geosciences in here. So what we're going to talk about here, like I said, you're going to learn sort of fundamental concepts of the geosciences. And you can think about sort of there's different sort of parts of the Earth. There's a solid Earth, which is things like the lithosphere, deep structure of our planet that we'll talk about. There is the interaction basically of the hydrosphere, which are things like the oceans, the biosphere, which are life on our planet, the atmosphere. All of these things interact together, and life has changed basically our planet, the physical characteristics of our planet over time. We'll also talk about surface processes, things like sort of climatic variation, how you get different geologic processes in different climates and so forth. I'll talk about some of the basic characteristics of common rocks and minerals. And like I said, this is really sort of the language by which a lot of geologic processes are described and how we understand them. I hope you'll gain an understanding of what science is, how scientists work, gain an appreciation for the complexity and beauty of our planet, sort of wonder of on our sort of this amazing planet that we live on is sort of an important thing. And then hopefully we can also think about sort of this concept of sustainability, where Earth resources come from, and how humans interact with our planet. Okay, so my name is David Ferris. I'm your instructor here. My office is in Graham Hall 104 in here. And so probably the best way to contact me is through email or through the Canvas messaging service in there. I've got my office phone in there. If I'm in my office, I'll answer my phone, obviously, but email is probably a better way to get a hold of me. My office hours are going to be 9 a.m. to 11 a.m. on Tuesday and Thursday, but I can also be reached many other times. And if you want to set up a meeting with me, I can meet in person. I can also be reached at WebEx, and I've got sort of my personal room in there. Just note that this personal room meeting is different. It's a different address than what these lecture recording sessions are in. But I'm happy to meet with you anytime to talk about really any aspect of the course. Okay, so about the lecture, I've already mentioned this, but the class is an asynchronous online course, meaning you're not required to come to attend the lectures live in here, but they will be, I'm going to be recording them on Monday and Wednesday at 10 a.m. here, and you can ask questions, interact, but then the videos will be then uploaded to Canvas, and you can then watch them. There's a textbook that's associated with the course, and this is The Essentials of Geology, 7th edition by Stephen Marshak in here. So you can get a physical copy if you like that. There's an ebook in here that's also available, somewhat cheaper in here. And basically all the material in the course is going to be present in the PowerPoint lecture slides and so forth, the lecture videos, but the various topics are keyed into the book, and the book provides basically another avenue for understanding this material. And so I think it's useful in that regard. Okay, so how you're going to be graded and evaluated in this course. is it's somewhat an exam-heavy course. There are 3 different exams. There's midterm 1, midterm 2, and a final exam in here. Collectively, the exams were 65% of your grade. Midterm 1 is 20%, midterm 2, 20%, final exam is 25%. I'll be having these mini quizzes, which they're timed quizzes that will be posted on Canvas that pertain to individual lectures. They'll be short, basically quizzes that will give you maybe a minute or 2 per question, and then you'll get 3 or 4 questions on sort of individual lectures. The goal of these things is to basically make sure that you're sort of watching the lectures and sort of staying up to date. And then there'll also be learning activities, which are basically these series of question sets on particular topics, and those will be happening periodically throughout the semester in here. If you miss an exam, you want to tell me about it. There'll be an exam window because this is an online course to take each of the exams, so hopefully that won't be as much of an issue, although sometimes people misinterpret the scheduling instructions on Canvas for exams. But if you miss something, please tell me as soon as possible. Ideally, if you're going to miss it, you tell me beforehand in here. Okay, so basically, you want to sort of participate in the course. We have basically a virtual classroom in here. All want to sort of get along in here, and so that's an important thing. This sort of on time to class thing, like I said, because of the virtual nature of things, is not quite really as relevant in here. But if you're interacting with people through discussion boards, things like that, you want to be civilized, respectful. We want to make this basically a welcoming environment for everyone in here. Comment on sort of academic integrity in here. A fundamental thing is that you want to do your own work. If you're found to have undertaken sort of acts of cheating, plagiarism, falsification, attempts to cheat, things like that, basically this is an academic integrity violation, and we will follow the basically steps for dealing with this they're outlined at sort of the Office of Student Rights and Responsibilities in here. Basically, potentially, if you're found to have, or if you're suspected of having one of these violations, albeit informed, you'll have time to respond to that. But we'll follow basically the sequence of steps that's outlined at the Office of Student Rights and Responsibilities. Ultimate sort of consequences of these are things like an F for the individual assignment, could even be sort of separated from the university for very extreme examples of this. Basically do your own work and it shouldn't be an issue. If you have any sort of disabilities, ECU seeks to fully comply with the Americans with Disabilities Act. If you need basically things like sort of additional time for exams and things like that, or any other sort of disability support, there's a Disability Support Services office. Contact them, and typically then they will contact me about whatever is your sort of particular situation in here. This is a general education course in here. One of the purposes of general education courses are to increase basically your breadth of knowledge, and so that's one of the things that we're aiming to do in this course in here. Let you read sort of all of that verbiage in here on sort of your own time. And then the other thing that I'm going to add to this sort of syllabus, not quite there yet, is a series of what we're going to be doing on each of the different sort of lecture periods throughout this semester. And so that will be, and I'll probably talk about that during the next lecture period on Wednesday. Okay, so stop sharing that. Okay, so the next thing we're going to move on to is the lecture for today. Should we ask any questions on the syllabus here? Okay. And okay, So this is our first lecture in here. And what we're going to be talking about is really the nature of science in here and the scientific method. But what I've shown here is this is basically a picture of the Earth in here. It's a digital elevation model of the Earth. And one of the things that you see is that there's sort of two basic colors in here. There's blue, which are the ocean basins, and there's this sort of green to yellow to red, which are the continents. This is sort of a fundamental part of the Earth. And it's one of the things that's sort of unique about our planet. And so no other planet in our solar system has things like continental crust. And so rocks like granite, which are really common on Earth, are actually scarce in other parts of solar system. And one of the reasons for this is we've got a dynamic, active planet in here. But it's good to know some of the basics about where we are. And so we are in eastern North Carolina in here, which is the eastern part of the North American continent, but we're sort of in the middle of the North American lithospheric plate. And the surface of the Earth is divided up into a number of these sort of lithospheric plates. These are plates that move around on the surface of the Earth. And where they interact, they generate things like earthquakes, volcanoes, some of these dynamic aspects to our planet. But an individual lithospheric plate contain both continental crust, which is rocks like granite, high silica, and rocks like basalt, and oceanic crust, contains these more dense rocks, or like basalt in here. And the lithospheric plate contains both of these components in here. And so the North American lithospheric plate actually begins at the Mid-Atlantic Ridge out here in the middle of the Atlantic Ocean in here. And so we're sort of in the middle of this, but we're in the transition between these two different components of the plate. And we'll talk more about this throughout the semester in here. Okay, so really our goal here for this lecture is we're going to be talking about the scientific method and really how it works. So the question is, what is the scientific method in here? And science is not basically a sequence of facts. It's really a method by which we can better understand the world in here. And it's proven to be amazingly successful. And as people have employed the scientific method over the last several hundred years, our understanding of how the world around us works has gotten better and better. And our ability to make predictions about sort of the physical nature of our planet, physical nature of our universe, has also gotten better and better. And this has allowed us to basically increase our level of science and technology. And this has increased our standard of living, really in a revolutionary way. And so science is really the use of observation, experiment, and calculation to explain how nature operates. And so it's a method, not sort of a sequence of facts in here. And scientific method, like I said, it's a sequence of steps that leads to more accurate predictions about how the world works. And so that's an important thing to remember here, that it's sort of this method of analyzing the world, not sort of a sequence, a specific set of facts. What sort of the facts about the world, or that what science says in terms of how the world works, changes over time in here. And so how this works is, if you start basically at knowledge zero, you don't know anything about a particular field, first thing you do is you go out and you make some observation about the physical world. And then you invent a hypothesis. This is really an educated guess as to why those observations exist. And then you use that guess to make an inference about, or basically a prediction about what's going to happen at a different time, different place. And you see if that's true or not. You try to test that hypothesis. And if your hypothesis passed that test, then you gain confidence in that particular hypothesis. If it does not pass that test, then you have to modify your hypothesis. And so there's sort of this loop in terms of how science works in here. And so you observe something about the world, you speculate on why it is, you test that hypothesis, you modify it, and then you repeat. And so this is a geoscience course. And so let's say you don't know anything about sort of the composition of our planet. So you go out and you start making observations. You look at basically the ground underneath your feet, and you see that there's some certain type of soil there. You go someplace else, you see there's some rocks that are exposed there. You describe what's there. And then once you have made enough of these observations, you can start to make predictions about, okay, why do you have these particular rocks in a particular location, or where you might see sort of another type. And you develop basically a model sort of in your head for why these things exist. This is sort of your hypothesis. And hypotheses can either be qualitative, meaning they're sort of verbal descriptions, or they can be quantitative, meaning that you fit basically, say, mathematical formulas and so forth to them. Then you test your hypothesis, see if it passes it. If it doesn't pass it, then you need to modify your hypothesis and test it again in here. And so over time, the predictive power of your hypotheses hopefully grows greater and greater in here. Okay, so it's good to have an understanding of what a hypothesis is. A hypothesis is an explanation involving natural occurring processes to explain a set of observations. This is sort of a key thing, that science deals with naturally occurring processes in here. And science makes an inference that basically everything that we see around us is naturally occurring. There's different ways that scientists can create hypotheses or test them. One is you can do an experiment in here, say a simple experiment. So you have a ball, you drop it. You could predict basically the time at which the ball will hit the floor from a certain height in here. And this is something that you could test. And this would allow us to gain some understanding of, say, laws of motion and gravity and things like that. Other types of hypotheses are more difficult to do these simple types of experiments on. And so the sciences are one of these types of fields that oftentimes, if we're trying to understand our planet, we can't make basically a separate planet and run basically the entire history of our planet, because it's taken 4.5 billion years for that to happen. And so a lot of geoscientists use natural observations in here to test hypotheses. Another thing that geoscientists do, because these are somewhat unconstrained environments, oftentimes you have multiple working hypotheses, or you generate two different hypotheses that are essentially competing with one another in here. And you see which one better describes sort of future observations. Okay, so once a hypothesis has passed many tests, it becomes a theory. Now, a theory is really no different than a scientific hypothesis. It's really just sort of a nomenclature issue. But in scientific sort of terminology, a theory is a more supported hypothesis than just sort of a hypothesis itself. And so we can have ideas that have things like the theory of plate tectonics. And this is the idea that we've got all these plates move around on the surface of the Earth that basically tell how many aspects of our planet function. And this theory has proved to be quite successful in basically saying why you get earthquakes in a particular location, or why you get volcanoes in a particular location. One of the predictions of basically the theory of plate tectonics is that in the past you had these supercontinents, where the continents were together in the past. You had the supercontinent of Pangaea that existed, say, about 250 million years ago, and that South America and Africa were once part of the same continent. And so this is a prediction that can be tested by basically the rock record in here. Okay, so scientists have more confidence in scientific theories because they've been tested and they have passed these various tests in here. But sort of a key thing is that these are not fundamentally different. They're still just hypotheses in here. Basically, everything in science is a hypothesis. But some of these hypotheses have greater basically quantitative predictive power to them. The highest level of these would be scientific law. These would be basically scientific hypotheses in which you've got sort of a quantitative framework that you can make very precise predictions of things. And things would be like the law of gravity. And so we can predict using our understanding of sort of the laws of gravity. We can send basically spacecraft that has to deal with sort of the gravitational fields of multiple planets, our sun, and you can end up many years in the future at particular locations in here. And this would only be possible if we have a reasonable understanding of basically the laws of gravitation in here. But once again, scientific law and hypothesis are not fundamentally different from one another. And there's nothing that says in the future that we might not come up with a better description of particular phenomenon. However, that better description needs to incorporate all of basically our past observations. And so in some ways it becomes more difficult to come up with a new hypotheses because there's this body of observations that they have to basically make better predictions than basically your past hypothesis. Another thing about science is that science assumes the natural world behaves in a consistent and predictable manner. This is a postulate, something that you sort of begin with for science, but to an amazing degree, this is proved to be true in here. And so the world around us can be described by basically the laws of physics. So something that would be separate from this would be supernatural entities. And so science can't really say anything about supernatural entities because supernatural entities don't basically follow the laws of physics in here. So that's something to be separate from science itself. There are also sort of groups of human knowledge that attempt to sort of cloak themselves in the language of science because science has been basically successful at making various types of predictions, and it's been successful in moving basically our society forward. And so pseudoscience are things that are not science, but make themselves sort of seem kind of like science. And these would be things like astrology, which is making predictions basically on the future based on sort of star patterns, telekinesis, moving things with your thoughts, phrenology, basically describing people's intelligence and personalities by the shape of their heads, things like ancient astronauts that built the pyramids. These are sort of pseudoscience, things that don't really, that do not follow basically the scientific method, but cloak themselves in some of the language of science. And so you need to be careful for distinguishing science from pseudoscience. And how you do this is that good science must be falsifiable. And so this is really sort of a key thing here. It must be capable of being proven wrong. And so you must frame scientific hypotheses in a way that is capable of proving that hypothesis wrong. And if you can't do that, then it's not science. Then it's more basically sort of philosophy or something else in here. And so that's, if you take one thing away from this lecture, this is what you want to take away. That good science must be falsifiable. Can also think, can science really ever prove anything? And to some degree, you cannot come up with sort of your ultimate proof of something, but you can gain essentially statistical confidence that a particular prediction will come out in a certain way. And so say, for instance, you have an understanding of the laws of gravity. If you take a ball, throw it up into the air, and you predict basically how it's going to come back down. And so you do this once, you see what happens, and you can predict it. If you do it multiple times in here, you don't really know that it's going to behave in a certain way, but you gain greater and greater statistical confidence in here. And so you never absolutely prove something, but you gain confidence that you have not falsified a hypothesis in here. Okay, so just to emphasize this once again, a good hypothesis is presented so that you can prove an experiment or an assertion false in here, that it must be falsifiable. Okay, and we've got a couple of examples of this. So we've got our snorg hypothesis here. And say you get up in the morning and all of your socks seem to have disappeared. And so you hypothesize that there's an invisible snorg in my closet that is basically eating my socks. However, snorgs are invisible. They have no smell. You can't touch them. And so there's no evidence that a snorg exists, except basically you're missing socks in here. This is not a falsifiable hypothesis. And so your snorg hypothesis is not scientific because you cannot prove it incorrect in here. Basically, there's the negative snorg hypothesis, which you could say that snorgs do not exist. And this is scientific because you can disprove it by catching and basically showing that a snorg exists. And you can do similar types of things for, say, a Yeti or the UFO or the Loch Ness Monster, that basically the scientific hypothesis would be that these things do not exist, and then you can show that they do exist by basically producing them in here. Okay, we've got some other falsifiable statements. You could say that all swans are black. You can disprove this by finding a white swan. You could say that water ice always melts at 0 degrees Celsius, and this could be disproved by measuring that it melts at another temperature. And this statement is actually true here, but with certain conditions. Basically, there's a pressure component to this. If you change pressure, say if you go up on top of a mountain where atmospheric pressure is lower, you'll change this a little bit. Also, it's dependent on the chemical purity of water. And so if you add various solutes and things to water, you can change the temperature at which it freezes. And this is one of the reasons that people put salt on the road in the winter in here. You could also say that heavier objects fall faster than lighter ones. And you could disprove this by showing that they fall at the same speed. A classic example of this is if you take a bowling ball, you drop it, and then you take a feather and you drop it. If you do this in basically the surface of the earth, the bowling ball is actually going to fall faster than the feather. But the reason for this is that that statement discounts, doesn't take into account air resistance. If you drop both of these in a vacuum where there is no air, basically they'll fall and accelerate at the same rate in here. Now, scientists are also human in here. And so they're subject to the same types of human sort of problems and issues that any human is basically deals with in here. And so you've got human egos. Say if you work on a particular idea for 20 years and then somebody proves it wrong, sometimes people have a great difficulty letting go of these ideas because they've just spent the last 20 years of their life working on it. And so they can't accept that it's falsified. And so sometimes you literally need to wait for certain people to literally pass away and die before their ideas can be fully replaced. There's self-interest. Sometimes people's livelihoods depend on certain ideas working. If they don't work, then they're in trouble. There can be political conflicts. Say if you cannot work on certain ideas, or if you can't work with people from certain countries, this can cause issues with sort of the dissemination of scientific knowledge and disproving certain ideas. There can be language barriers, or these are less extreme than they are today because of sort of universal sort of translation. But say if I need a book that's written in Chinese and I can't read Chinese characters, then that's not really happening today, for instance. Science is also dependent on the type of tools that you have. And say for instance, if understanding a particular problem requires an understanding of the trace element geochemistry, and you need to have a good understanding of basically the part per million of, say, lanthanum in a particular mineral in here. But all you have is a magnifying glass and a hand lens. You're not going to be able to address that scientific problem really at all. And so the types of scientific tools that you use allow you to address different types of scientific problems. And say if you have just a hammer and you need to measure basically, say, an isotopic ratio of, say, uranium lead in a particular rock to understand its age, then that's not happening in there. And so the types of questions you can ask are limited by technology. And as technology increases, then this allows you to ask different questions. And so as science moves to sort of higher levels, this allows us to ask sort of more detailed questions. And so there's this iterative feedback loop between science and technology, that increasing our understanding of science allows us to have a basically greater technological understanding of the world and create more efficient tools. And having more efficient tools allows us to have a better scientific understanding of the world. You can also think about this idea of truth. Is there a fundamental truth that science is getting to? And this is probably not the case with science. Science deals in hypothesis testing, but each individual hypothesis is not necessarily the final word in science, although there's theoretically some underlying reality that science gets closer and closer to, sort of the further on and the greater number of basically tests that a particular hypothesis has withstood. But there's nothing that says in the future that we won't come up with sort of a better explanation. And we'll talk about this idea of scientific paradigms here in a second. Another thing to think about is there's Occam's razor. This is another idea for distinguishing between two hypotheses. This is basically, the idea is that if you have two hypotheses that have equal predictive power, you should go with the one that's somewhat more simple. This is more of a tool that has proven to be effective in the past, but there's no particular reason that this is actually the case. But it's better to test sort of a simple hypothesis first and then move on to sort of the more complex one. Another thing with science is you want to separate observation from interpretation. Observations are observable facts that should be repeated from one person to the next. And it shouldn't matter who's making the particular observation. Then you have your interpretations, which are basically hypotheses that you invent to explain your observations. These can differ from one person to the next. And so you want to make sure that you don't mix these things. And particularly for people starting off in science, mixing observation from interpretation is a big thing that people struggle with. Okay, so scientific ideas and hypotheses are framed in particular scientific paradigms. A paradigm is this overarching theory in which a lot of interpretations or a lot of observations are interpreted. And periodically there's changes in scientific paradigms. I'll give examples of this. Okay, so in the geosciences, our current paradigm is plate tectonics. It's this idea we've got a limited number of plates that move around on the surface of the Earth, and these describe basically how our planet functions. In the past, and really not that long ago, say 50, 60 years ago, we had a different scientific paradigm known as geosyncline theory. And this is primarily that mountain belts move sort of up and down, but didn't have really big lateral movements in them. In astronomy, sort of if you go back to the beginning of modern science, we had this debate on the heliocentric solar system, which is the idea that the sun is at the center of our solar system, versus a geocentric solar system, which is the idea that the Earth is at the center of our solar system in here. In physics, in sort of the 20th century, we moved from a Newtonian physics to this idea of relativity and quantum mechanics. And so it was found that at very high speeds, as you get close to the speed of light, or if you go to very small scales, the Newtonian physics, that's the physics essentially described by Isaac Newton, begins to break down and doesn't effectively describe the world in here. And so these are sort of our current paradigms of physics in here. Biology, the current paradigm is evolution by natural selection of inherited traits. This is what Charles Darwin came up with in the 19th century in here. And sort of a past paradigm was Lamarckian evolution, where you have heritability of acquired traits. And the idea would be that, okay, a giraffe has a long neck because it stretches to reach sort of fruit. And so its neck gets longer over its life, and then it passes that longer neck on to its offspring. And that's, for the most part, not the case in terms of how evolution works. So those are examples of different scientific paradigms and how they have changed over time. So we can think about, why do scientific paradigms change? Basically, you have a paradigm exists in the first place because it has a certain degree of success in describing observations. But if you have certain sort of edge cases and so forth that can't be explained by a particular paradigm, eventually observations on these things might become great enough that you need to overturn the entire structure. But overturning a paradigm is difficult because people get very invested in these ideas. And so sometimes we literally need to wait for people to die out, like I mentioned before a new paradigm can be fully accepted. Okay, so that's really the end of our scientific method here. I'm going to talk a little bit about geology and the geosciences and where these things fit in. So if we look at branches of science, you can make two big sort of groupings. You've got physical sciences, and we have life sciences. Nominally, the earth scientists, which include geology in here, are in the physical sciences. But there are branches of the geosciences that are sort of in between life sciences and physical sciences. And so we've got things like geochemistry, geophysics, sort of structural geology, igneous petrology, sort of how rocks sort of form, how they are deformed, basically what is their basic structure of our planet, and so forth. There's certain branches of geology like paleontology that are really involved in studying past life. These are studying fossils and so forth. And so you need to understand basically the sedimentary rocks that they formed in order to really fully understand these fossils. But paleontology is really looking at, say, the past history of life. We've also got things like environmental sciences, which are really at the intersection of sort of the earth sciences and life sciences here, because our environment is influenced by living creatures and so forth. But if you're asked the question, which branch of science are the earth sciences in, you'd normally want to say the physical sciences in here. Okay, so geology is the study of Earth and the planets. There's some things that are unique about this. There's a huge amount of time and space that this covers. So our planet formed 4.5 billion years ago. So a huge length of time. This is one of sort of the big discoveries of the 20th century, really. What is the actual age of our planet in here? Are these geologic systems formed by the interaction between, basically, you've got your solid earth, you've got your oceans, you've got your atmosphere, you've got living organisms. All of these things interact together. Rocks and sediments are really the language by which we can tell the history of our planet. And humans, as we're finding out, are actually geologic agents in and of themselves. We are changing the planet. So we can think about time scales. You've got sort of the age of our universe itself, which is, say, 13 to 14 billion years. The age of our solar system and planet, 4.5 billion years. And we can also think about things that are happening on very small timescales, like the timescales for which seismic waves pass through the Earth, sort of seconds to minutes and so forth. We've also got huge length scales. We can look at things that happen on a microscopic scale within individual crystals to things that happen on the scale of the entire planet in here. And so the surface of the Earth is really a product of all of these sort of different interacting things. And so we've got the solid Earth, we've got things like erupting volcanoes, we've got things like life that are changing our planet in here. So we've got an erupting volcano and coral reef in here. Change is happening all the time, but humans are also powerful agents of geologic change in here. And so this is a big road cut being cut through a jungle in here. We've got the Panama Canal. That's a human-induced, basically, river that goes between the Caribbean and the Pacific in here. Humans build huge cities that can spread over hundreds of kilometers or 100 kilometers across that are visible from space. And so this is the Los Angeles basin. All of this gray that you see here is paved areas. It extends for about 100 miles from basically the Pacific coast to the mountains in here. And so this is a human created basically geologic layer that would be present in our Earth history, that people would be able to see that exists millions of years in the future. Okay, so by studying rocks and minerals, this can tell us about basically the history of our planet, but we need to know how to read that language. Different things that geoscientists do, they can find and manage natural resources. They can teach us about geologic hazards. They can understand how the Earth works. They can tell us about Earth history. They can tell us about different natural environments. Geoscientists are involved in finding most of the energy resources that allow us to run our society. And that over the last basically 100 years, there's been this huge increase basically in energy consumption. And here, a lot of these come from fossil fuels. There are also renewable energy resources that are becoming sort of increasingly important in here. But being able to find these things and exploit them is something that geoscientists do. And so they're involved in basically the very basic parts of our economy through which nothing else would work. Study natural hazards. There's a landslide here. Can understand basically how the Earth works. And so we've got a cross-section through our planet with our inner core, outer core, the mantle in here. Our planet is dynamic, it's alive. And understanding how it works allows us to better live on our planet. Understanding basically the past history of our planet. So we've got the Earth began about 4.5 billion years ago. Life, first evidence of life, occurred around 4 billion years ago. But throughout most of Earth history, life is single-celled organisms. And it's not until about 540 million years ago, maybe about 600 million years ago, that we tend to get large sort of multicellular life. Humans have really only been around for a very small fraction of the Earth history in here. And so understanding our place in basically this history of life is one of the things that geosciences can tell us. So here we've got sort of a big waterfalls, Niagara Falls. Understanding sort of resource use and how to use these both sort of responsibly and sustainably is something that geoscientists are involved in. This is a big phosphate mining sort of settling pond in Florida. There's also a big phosphate mine not that far from Greenville in here. But say after you extract an individual resource, so geoscientists are involved in finding these things, figuring out how to extract them, but then also involved in figuring out how to take these sites and return them back to sort of natural environments. And so here's this mine that's been reclaimed to sort of grasslands and then further reclaimed here to forest environments in here. And so being able to sustainably use resources is a critical thing. And something that's increasing as humans become sort of more and more numerous on this planet. There's more than 8 billion people on our planet. We're using more and more resources every day. And so we really need to function as basically effective stewards of our planet to be able to continue to live here and have high standards of living. Okay, so overall, we want to learn this semester how basically our planet works and how these different planetary processes are interrelated with one another. And so we have the atmosphere, we have the oceans, we have the crust, we have the mantle sort of deeper within our planet, and then we have the core. And all of these things interact together here. And that's what we're going to be covering and dealing with this semester here. And so that's basically we've gotten to the end of our lecture here for today. So I guess we finished a few minutes early here, but I will stop here and I will let you guys go. And this will be posted on Canvas so you can review it. And then also we'll be having the next lecture, a recording session on Wednesday at 10 a.m. So anyways, hope you guys have a good rest of the day, and I will talk to you later. Bye.
Thank you. Bye.